8th grade. We are into transforming exponential expressions today. This is module 9.4, and let's look at our learning target. I can use the properties of exponents to transform expressions for exponential functions. So let's quickly review what we did in module 9.3. So we talked about our exponential growth, exponential decay, and compound interest. So let's quickly rewrite the formula for exponential growth. And for that, I had y is equal to my initial value, which is a1, which is the 100%, that's the whole, plus the interest rate, the rate which is in the decimal form. And then we are putting this entire thing, to the power of t, which is the time. And this was my exponential growth. Okay, then let's talk about what compound interest was. Again, a compound interest is a type of exponential growth because everything in compound, so this is my exponential growth, okay, and then my compound interest. Okay, so this compound interest is exponential growth. It has exactly the same formula. The only difference is that we also need to see that is the amount compounded, is it compounded annually, bi or semi-annually, is it quarterly, so or monthly. So that is what this compounding is. So the rest of the formula is the same. And so then we have n times t, how much it's compounded times the time, okay? So in today's lesson, where we are transforming exponential expressions, we might be given two different types of bank accounts or something where the interest rate is different. And one might be compounded annually, one might be compounded monthly or quarterly, etc. And so what we have to do is we have to put both of them into the same format of compounding to see which is the better interest rate. Okay, so let's go ahead and do some examples on this. So here I have a question which is written out, and so let's look at this. And we are talking about banking. Sayville Bank offers a savings account with 0.15% interest compounded monthly, okay? And the second local bank offers a savings account with 2% interest compounded annually. So you can see one is monthly, one is annually. And in order for us to compare the two accounts, we need to see that we are comparing the rates with the same compounding frequency. So either we are going to compare them by changing them both into annual, or we are going to change both into the monthly to see which has the better interest rate. Okay, so let's see what the rest of the questions. We already seen Sayville is 0.15% and the second local bank is 2%. Okay, but one is compounded annually, the second one is compounded annually, and the first one is compounded, monthly. Okay, so all right, so here's the rest of the question. It's saying write a function to represent the balance, say, of a savings account after t years at second local bank. Then write an equivalent function that represents monthly compounding. So we know that the second one, what was the rate? It was 2%. And for the second local bank, once again, what was my interest rate? My interest rate was 2% for the second bank, okay? Because talking about the second local bank, it was 2%. And it was done annually, okay? It was compounded annually. So that is once a year, okay? So what we're going to do is we are going to, first write out the equation for exponential growth because we know that y is equal to my initial amount, right? Then I have the 100%, which is 1, plus r raised to the time. Okay, so for the second one, we had, let's assume that for convenience, let the initial amount of investment be $1. Okay, so okay, you can see it. Let initial amount, which is A, be equal to $1. Okay, $1. So we are going to then put that into my equation. So we are going to do, okay, balance A. So A to the function of t this is equal to 1. And I'm going to put 1 plus what is my 2% as a decimal. This is going to be 200th. Right? So I'm going to do and 200th t, right? Because I'm showing my exponential growth. Okay, so this is my exponential growth because the interest is going up exponentially, right? And so then I'm going to simplify and I'm going to get 1 times, of course we took that as 1 for a reason, so I'm going to get 1 and 200 t. So here is my equation. Okay, now the next thing we are going to see, this is done annually, but to write a function, we have to make both of them the same compounding. So the other bank, it was done monthly. So that means the compounding is going to be 12 times in the year, right? So therefore, in this case, it is 1t, but I have to change this to 12t, okay? Over here, it is 1t because it is compounded annually, but I have to change this for my monthly compounding. I have to change this to 12t. Okay, so I'm going to write out my original function, which is here, and then what I know that 1 year is equal to how many months? Okay, so I'm going to 1 year is 12 months, and then I have to do this for my, for 12 months, right? So 1 year is 12 months, and I have this only for 1t, but I have to change it to 12t. So this is what I'm doing. Okay, so I'm going to rewrite this, and I'm going to say is equal to, we have 1 and 200, and then I am going to put the exponential part of what I have over there, okay, which is 1/12 times 12t. Okay, I have got to change, remember, the 1t to 12t. So then I'm going to use the power property, and I am going to do A is equal to, and I am going to move this to this because I can multiply the powers, right? So I'm going to do 1 and 200 raised to 1 to the 12th power, and this is 12t. See, now I have 12t. And that's what I needed to get to. Okay? And if I look at 1 in 200, 1/12, what does this actually mean? Okay? This means that this is going to be the square root of, not square root, the 12th root of 1 and 200. Right? Which is about, so we're going to say approximately, and this is approximately when I'm using the calculator, and it's an approximation because now I'm rounding. right? So this is going to be 1.00165. So when I do this part, I get this. And so therefore, it's approximately 1.00165, and I have the exponent 12t, and that's what I was trying to get to, because earlier it was annual, so it was 1t, right? But in this case, I've got to put it, because it's 12 compoundings in a year, I've got to do 12t. So this is what I am going to do next. So now I can see that the effective monthly rate offered by the second local bank is about, and if I change this to a percent, so this is my 1 plus something, right? So if I just look at the fractional part, that is telling me the percent, which is my R. Okay, so let's move this and just look at this part. So if I look at this part and I am changing this to a percent, a decimal to a percent, I've got to move it 2 places to the right. So therefore, my percent is going to be 0.165% for the second bank. And that means that it is slightly more than the 1500%, because the other bank, which is Savewell Bank, was offering, they were offering this percent. So if I'm looking at both of them, which one is higher? This is better, because you're going to get more money, right? So therefore, the second bank is a better choice. And so this is how we compare. Make sure that you are compounding with the same frequency, and then you can check out which is the better interest rate. Okay? So once again, at the end, we know that this is 1 plus the interest rate. So when you are changing it back to my interest, don't look at this, just go 2 places to the right, because this is the one which is added on, the 100%. Okay? And that tells you which is the better interest. Now what we're going to do is we're going to go back and look at the first bank. And you're going to write, again, we are comparing annual rates. So we are going to look at, we again had Savewell and we had the second local bank. Okay, Savewell Bank, what was the percent? It was offering was 1500%. That is what this one was offering monthly. Okay, Savewell Bank was compounding monthly. Okay, so this was monthly. Okay. So now what the question is saying, let's look at the question. And it is saying that compare annual rates, write a function to represent the balance A of a savings account after T months at Savewell Bank. Then write an equivalent function that represents annual compounding. Okay, so we know that Savewell was done monthly. That means it was 12 times, right? So now we have to change it to your time is 1 year. So from the monthly to annual, that's what we are changing into. And we know that the Savewell the Savewell interest rate was 1500%. So let's go ahead and write our equation for exponential growth, which is y is equal to a1 plus r raised to the t power. All right, so over here, we are going to say y is a of t, okay, is equal to, what is my a? We are going to assume that it is $1 again. Investment is $1. Okay, investment is $1. So we are going to use that, the initial amount. So this is 1 plus, what is 1500% as a decimal? It is going to be 0.0015, because we moved the decimal 2 places to the left. and raised to the t power. Okay, and so therefore a of t is equal to, we have 1.0015 raised to the t power. So here is my equation after I simplify it. Now, the next thing, this is representing the balance of a savings account after t months. Okay, this is t months. Over here, it is monthly, remember? So it's t months. But what do we need to do? We need to compound it yearly. So since there are 12 months in a year, the exponent should be, this should be 1 over 12, because now we are compounding it monthly. Okay, so from annual, we are going to monthly. Okay, so for that, we are now going to, of course, write the original function, which is already written out over here. And I know that 1 year is equal to 12 months, right? Times, we know that we have 1 year over 12 months. So 1 year over 12 months. And that's what we are trying to get to. Because right now, this is in this format. But we have to change it to 1 over 12 because there are 12 compoundings in a year if it is done monthly. Okay, so my exponent now, my exponent needs to be 1/12 t. Okay, so this should be 1/12 t outside. Think of the other one, what we had just done. That was being changed, to my year, that was yearly. Right? So that was being changed to how many times? That was going to be changed to 12t because there are 12 months in a year. But in this case, the yearly is being changed to the monthly. So they are 1/12. So that is why the exponent is changing the other way around. Okay? So now what we are going to do is we are doing a of t is equal to 1.0015. Okay, and so then we are using the same thing, that what we do, 12 times 1/12 t, and this is what we are trying to get to. Okay, and so then when I look at this, I can do the power of a power property, and I do a is equal to, so a of t is equal to 1.0015 raised to the 12th power. Now look, I have my 1/12 t, and that is what I'm trying to get to. Okay, and then when I solve this, I'm going to solve this part with a calculator, I am going to get a of t is equal to, I'm going to get 1.0181, and then this is raised to the 1/12 t power. Okay, so now from this expression, we can determine that the effective annual interest rate of Savell Bank is about, so now we're taking only this part. Remember, I said to focus on the decimal. So for Savell Bank, it was 0.181. And so we're changing that decimal to a percent. So we are going to go 1/2, which gives me 1.81%. Okay, which is less than the 2% interest rate offered by the second local bank. And the second local bank was offering 2%. So, which is the better one? The second local bank, because that's giving a higher interest. So this is basically how we are doing transformation, between the exponential expressions, depending on the compounding. Remember, to compare, we have to change it to the same compounding method, whether it's monthly or it is annually or it is quarterly, etc. So let's do one more example just to understand this concept. All right, let's look at this question. Investing. Camille is planning to invest money in a savings account. She is comparing the interest rates of savings account at two banks. Bank A offers a savings account with 2.1% interest compounded annually. Okay, compounded annually. So, that's the first thing we need to look at. This is compounded annually. And this is my interest rate. Bank B offers a savings account with a quarterly compounded interest rate of 0.8%. So we're going to write a function to represent the balance A of Camille's account after T years through Bank A, assuming an initial investment of $1, and then we're going to write an equivalent function that represents quarterly compounding. We know that our equation for exponential growth is y is equal to a 1 plus r, and we have t. Okay, so for let's say y is equal to a of t. Okay, and so we have y is equal to a of t, and a, as we said, the initial investment is $1. So this is going to be 1 plus, what is my interest rate? My interest rate is 2.1%, which as a decimal, this would be 1, 2 to the left. So therefore, this will become 0.021. Right? So therefore, this is going to be 0.021, and then I have my t, okay? And so therefore, a of t is equal to 1.021 t. So now I have this equation written out. Now, we are going to write a function that represents 4 compoundings per year. Okay, hers is what? Annual. So right now it is what? It is 1t. But what we have to do is we have to make sure that because it's 4 compoundings, that has to change to 4t, which is going to be my power. So because of compounding, this has to change to 4t. Okay, because if I'm saying quarterly compounding, that means it's compounded 4 times in the year. Okay, so let's go ahead and we know that 1 year is equal to, let's see, 1 year is equal to, what do we have? We have our, so 1 year is 4 quarters, right? And this is going to be times 4 quarters, because we are trying to get it into our 4t. Okay, so what I'm going to do is I am going to write this again. A of t is equal to 1.02. Okay, and then I have 1/4 times 4t. Okay, and this is actually, this whole thing is like this, t. And then what I'm going to do is I am going to do the power of power property of exponents, and I am going to say a of t is equal to 1.02 1/4 power over here, and then what am I left with? 4t, and see, that's what I'm trying to change it to. Okay, and so when I do this, this basically means what? This means square 4th root of 1.02, and when I use my calculator, I am going to get a of t is approximately, because now I am rounding, and I get 1.0052 0.0052 raised to the power of 4t. Okay, so now I have written this out in this format. And which bank has the better plan? So if I'm looking at this one, in the other one, let's see, we have 800. So let me do that with a different color. So let me do that with blue. So I'm going to write the same exponential growth. Y is equal to a 1 plus r raised to the t power. And then I am going to say my initial investment is going to be 1. So a of t is equal to 1. 1 plus, what is my rate? It is a 10%, which as a decimal is going to be 0.008. Okay, and raised to the t power. And so therefore when I simplify this, I am going to get a of t is equal to 1.008 to the t power. Okay, and so this is an 8. Okay, so this is what I have right now. I have simplified it. Now we are going to write an equivalent function that represents one compounding per year. So, and we know that this one is being done quarterly. Right? So what we're going to do is we are going to change, we need one compounding per year. Since there are 4 quarters in a year, the exponent should be 1/4 t. So now we are going from our quarterly to our annual. Okay, so it's going to be, because there are 4 in a quarterly, there are 4, it was 4t, right? So we need to take it to 1/4 t, because annual is going to be for 1 year. Okay, so now let me go ahead and do that over here. And I am going to go ahead and write out this original function, which is a of t is equal to 1.008, and we have t, right? And so, and that is 1t. We know this is 1t because this is annual. And I am going to have to change this to 1/4 because that's what I need to get to, okay? And I know that 1 year is equal to 4 quarters times 1 year over 4 quarters. So therefore, I'm going to write this as a of t is equal to 1.008. And as I said, it has to be 1/4. So I'm going to do 4 times 1/4 t. Okay, and then I am going to do my power of a power, and I'm going to move this here. So a of t is equal to 1.008 to the 4th power. And now look, I have my 1/4 t over here. Okay, and then when I simplify this, I am going to get, where should I write it? Let me write it over here. A of t, and this I'm simplifying, okay? And I can round it after I get my results, and I get 1.032, 1.032, and as you can see now, I have my 1/4 t over here. Okay, so here is my effective annual rate for this one. Again, look at the decimal part only, and I'm going 1, 2 to the right. And so what is my decimal part over here? I'm going to get 3.2%. This one is 3.2%. Okay, and so we are looking at both of them, and this confirms that the result of part B, because 3.2% is greater than the annual interest rate at bank A. Okay, so we know that bank A had how much? It was this much. And this one has 3.2%, and so bank B has the better plan. Bank B has the better plan. Okay, and so that's basically what this lesson is about. You just need to change them to the same form of compounding, and then that is how you are going to see which is the better interest rate. And that's basically what this entire lesson is about. When I am using properties, and we were using power of power properties a lot over here, to transform expressions for exponential functions. All right, so that concludes module 9.4. Have a great day, everyone.